let's take some of that information we know and do some problem solving with the Diels-Alder reaction. First of all, so I've got two reactants here. Identify the diene and the dienophile. Right? Here I have a diene, but it is S-trans. Just a plain single bond in between and no rings that are tethering it, so we can at least attempt to rotate about that middle bond there. If I did it that way, I would end up with this compound. Right? You can just switch two of the groups like that. Or if I orient it in a little better direction for forming a six-membered ring, that's what it would be. So when I rotate that double bond, you're just interconverting. You're interchanging two of those groups there. Okay. Get a model kit and try that out if you can't see that rotation happening. This coming to here and that coming up through there by rotating that bond there. You'll need to do that because molecules will not always be drawn in the most reactive conformation. They're actually usually drawn in their most stable conformation, even though this is the only conformation that reacts in Diels-Alder. So 1, 2, 3, and 4 again. Reacting with the dienophile. Got a double bond with a methyl group, a C double bond OOCH3 attached to it in a direction that is trans-like to the methyl group. Let's call those 5 and 6, just the CC double bond. Remember what happens in a Diels-Alder. 4 joins to 5. 1 joins to 6. And then the double bond migrates to between 2 and 3. So product, you can always start by drawing a six-membered ring. I'm going to sort of color code it here so you can see where everything came from. Blue ones are our new bond that was formed. 1, 2, 3, 4, 5, 6. That'll help us add our functionality back in. Methyl groups on 2 and 3. And remember, the double bond will migrate to the middle of what was once the diene. Okay. 5 has a methyl group, 6 has a C double bond OCH3, but remember the stereochemistry is retained. So if I were to draw that methyl group going down, I would have to draw the C double bond OCH3 coming up. So a dashed line and a wedge line. As a trans product like that. I could have just as easily chosen to draw the methyl group coming up, in which case I would have put that other group going back. So it's only relative stereochemistry that's determined here, not absolute. We produce this as well as its enantiomer, in other words. So that's the product of that one. Let's look at this one. I have a C double bond C, then C double bond OCl, so that looks like a dienophile, right? Over here is a diene, so 1, 2, 3, 4. Let's redraw that diene as S-cis. Okay. You can always start by drawing a diene like that and numbering the carbons and then attaching whatever else was originally on it. In this case, those two methyl groups on 1. In this case, this will be fine in S-cis because carbon 4 only has hydrogens on it. If this also had a methyl group pointing inwards, that would be too unstable to be S-cis. So here's the dienophile. Let's redraw that. C double bond OCl. 5, 6. New bond between 4 and 5. New bond between 1 and 6. Draw a six-membered ring as a product. 2 new bonds formed. This bond was originally in the dienophile, so numbering 1, 2, 3, 4, 5, 6. New double bond between 2 and 3, right in the middle. Carbon 6 has C double bond OCl attached. 5 just has 2 H's, so there's no relative stereochemistry there. 1 has 2 methyl groups on it, so I can just draw those like that. And there's our product. So double checking your product to make sure you have a 6-membered ring, to make sure your double bond has migrated. That's why this numbering is so important. And then double check to make sure you've included all of the functionality that was on the diene and on the dienophile. Let's go backwards. Let's deconstruct a Diels-Alder product. If this is our product, let's figure out how we would make that product by a Diels-Alder reaction. So I can use a double-barreled retrosynthetic arrow to figure out what those came from. Okay? This is thinking backwards again. So if this is our product, let's figure out how we would make this. Well, first we have to find the 6-membered ring. Okay? Some cases that's easier than others, but this is bridged bicyclic. The 6-membered ring has to have at least one double bond in it. And if we look at all of our products, the double bond, we call that between 2 and 3. So let's do that. Let's just call the double bond in the product 2 and 3. And then that gives us 1 and 4 automatically. Now 5 and 6, we got a choice. Is it up here or is it down here? Remember, 5 and 6 came from the dienophile, which means it had to have some electron withdrawing group, like this C double bond O. So that's what the 6 carbons look like. Then what you can always do is draw a diene, like that. Just draw S-cis diene, draw a dienophile. Okay. That's the minimum that you need to do a Diels-Alder. So number those carbons, just like we've been doing. And then add the other stuff that's attached. Here's the new bond that's formed. I'm going to draw squiggles through it to show that it's broken in our retrosynthesis here. Okay. Since we're figuring out what things were used to make this. Carbon 1 and carbon 4 have a 2-carbon bridge between them, and in the original, there are those 2 carbons, right? Here's 1 carbon and another carbon right there. So that means, in this case, the diene was a 6-membered ring itself, right? Just like before, when we had a 5-membered ring as a diene, those extra carbons in the ring got pushed up above to make that bridged bicyclic compound, like the handle to the basket. In this case, if we got 2 carbons on the handle, that means our original diene must have had 2 other carbons joining 1 and 4. Okay? As for the dienophile, I have a C double bond OH attached to 5, a CH3 attached to 6, and notice they're not going in the same direction. Okay? If they're both cis to each other, they would either both be going down or both be going up like that. I'll circle them so you can see it here. Those are trans to each other in the product. So all you have to do is draw them trans to each other in the dienophile. Doesn't really matter which direction you go, just as long as you make them trans to each other. There you go. So if I took this diene, reacted it with this dienophile, this right here would be the product we would get. So in retrosynthesis of a Diels-Alder reaction, the thing you identify is the 6-membered ring, the double bond at 2 and 3 in that 6-membered ring. Okay? So that double bond in the ring orients you to where everything originally was. And so this is an interesting one. There's a 6-membered ring and 2 double bonds. Okay? So we have our choice here. The only other thing we have is COOCH3. That's an electron withdrawing group, so that must have been part of the dienophile. For instance, carbon 6 of the dienophile. If I do 1, 2, 3, 4, then the other double bond is between 2 and 3, like it should be in a Diels-Alder product. Okay? The 4-5 bond is the one that's formed in the Diels-Alder reaction. So our diene is pretty simple. Just normal butadiene. 1, 2, 3, 4. But now our dienophile between carbons 5 and 6, our dienophile can't just be a double bond, because in a normal Diels-Alder reaction, that double bond becomes a single bond. Our dienophile must have had a triple bond in it, because the triple bond can become a double bond in the product. So there was our two Diels-Alder reactants that can be combined together to make this 6-membered ring with 2 double bonds totally across from each other. Notice the double bonds are not conjugated in this product. They're across from each other. So that's a functionality you should be recognizing as requiring a triple bond as the dienophile. If I do my sort of faux reaction arrows, I can sort of imagine how that would play out. That makes the one double bond from the diene makes a bond to 1 carbon of the dienophile, then one of the pi bonds makes the new bond to 4, but the other pi bond remains behind. Okay? Normally, if I would have just had a double bond in the dienophile, that pi bond would have gone to make the bond, and I'd just be left with a single bond behind. Okay? So then I have the one migrating that way. So watch this functionality. These 2 double bonds in a Diels-Alder product must have came from a triple bond as the dienophile.